Good afternoon, everyone. Assalamualaikum warahmatullahi wabarakatuh and a very good afternoon to everyone. Can you see my slide?
Yes,
Yes.
doctor.
Yes, doctor.
Okay, all right. So hopefully you have already finished doing all the ELIP activity for learning unit 1. We have covered in the class on the basic terms used in analytical chemistry, and then we also covered on the 9 steps for quantitative analysis. We have also learned about qualitative analysis, and I have given you some homework or some tasks to do on ELIP regarding the quality assurance, and as well as some exercise on concentration, different units for concentration. So hopefully you have done all the activities on ELIP and all the exercises, as well as the study questions. So today I'm going to proceed with learning unit 2, which is on stoichiometric calculation. However, at the beginning of this lecture, I will also be covering on concentration units, so that we will have uh, some revision on what we are going to use during our stoichiometric calculation later on. Okay. Right, at the end of this learning unit, you should be able to explain and calculate molarity, molality, formality, normality, and other units of concentration. For example, parts per million, parts per trillion, parts per thousand, parts per billion, and so on. You should be able to explain dilution and solve problems related to dilution, and solve problems using stoichiometric approach. So in today's class, in 1 hour, I will be covering the theories and also some examples regarding these 3 concepts that you need to understand. But the exercise and the activities, you need to use the remaining 2 hours to do it. Okay. All right. When talking about concentration of solution, it's about the behavior of solution, which depends on compound itself and how much it is present. Okay, two solution can contain the same compound but can behave quite different because of the proportion of those compounds are different. This is what we call solution with different concentration. For example, if you have hydrochloric acid, which is 12 molar, we call it concentrated hydrochloric acid. If you compare it to a 0.1 molar hydrochloric acid, they behave differently. For example, the more concentrated one will be more corrosive, but the less concentrated one, like let's say 0.01 molar or 0.1 molar, it's considered a diluted acid. So they behave differently. Okay, because the proportion of HCl in the HCl solution is different due to the different concentration. Okay, you are going to use a lot of concentration in analytical chemistry. Okay, and they will be of different units, which require you to understand the unit conversion and also to understand the definition of each concentration unit. Now, we go to the concept of mole. Mole is also called Avogadro's number. Okay, this is the origination of mole. Avogadro's number 6.022. And a mole is defined as the number of carbon atoms in exactly 12 grams of carbon 12. Okay, so the definition is selected so that the formula weight in AMU and the molar mass in gram per mole have the same numerical value. For example, for carbon, the formula, the molar mass is 12, and we call it in 12 gram per mole, but it is also the same value for AMU unit, which is 12 AMU. Okay. So mole is the SI unit for Avogadro's number. Okay. 1 mole is equal to this value. Okay. For example, if we consider water, in water we have 2 hydrogen atoms and 1 oxygen atom. So 2 hydrogen atoms, when we times with 1 AMU of hydrogen atom, it's total 2 AMU, and for the oxygen it's 16 AMU. And if you notice from the periodic table, the formula, the molar mass for hydrogen is 1 gram per mole, and for oxygen is 16 gram per mole. Okay, so the value is the same. So if you have formula weight for H2O 18 AMU per formula, your molar mass is 18 grams per mole. Concentration can be expressed in many ways, but the most general definition is concentration is equal to the amount of solute over the amount of solution. Okay, so this is general definition of concentration. You want to determine how much solute is contained in a particular solution. Most common unit used is molarity. Molarity is defined as mole of solute per liter of solution. Okay, moles of solute per liter of solution. Okay, I think somebody is highlighting my screen. Okay, so when we talk about moles of solute, it is the amount of, it's the mole of substance in the solution. For example, when we talk about hydrochloric acid solution, hydrochloric acid is the solute and the solution is the hydrochloric solution. The solvent is water. So there are 3 different terms here. One is solute, one is solvent, another one is solution. Solution is the resulting of solute and solvent. Okay, solvent is a solution that you use to dissolve solute in order to make solution. Okay, for example, another example is when you prepare sodium hydroxide solution. The solute is sodium hydroxide pellets. The solvent is water, and the solution is sodium hydroxide solution. Okay. All right. Molarity refers to the moles of solute per liter of solution. For example, 1 molar solution contain 1 mole of solute in every 1 liter of solution. Okay. So here's the unit of molarity. How do you prepare 1 molar of solution? 1 molar of sodium chloride solution. So you are going to need 1 liter of 1 molar sodium chloride solution. Sorry, when you want to prepare 1 liter of 1 molar sodium chloride solution, you need 1 mole of sodium chloride, and you need to have 1 mole of 1 liter of solution. Okay, so how do you determine how much you need to weigh the sodium chloride in order to make 1 liter of sodium chloride solution? Okay, it's about determining how much gram you have per mole of sodium chloride. You go back to the periodic table and see what is the molar mass for sodium and what is the molar mass for chlorine. And for sodium chloride, it's the molar mass of sodium and chlorine combined together. It's 58.5 gram per mole. So this is how much you need to weigh sodium chloride solid in order to prepare 1 liter of solution. Okay, 1 liter of 1 molar solution. So because you have 1 mole of NaCl here and 1 mole of 1 liter of solution here, Na solution. Okay, you go back to the definition of molarity just now. Molarity is equal to mole of solute over liter of solution. So this is the mole of solute and this is the liter of solution. Okay, now let's go to example 1. Please prepare your pen and paper so you can try this exercise together. Okay, what is the molar concentration of sodium chloride if you have 0.5 mole sodium chloride in 1 liter of solution? So you go back to the definition of molarity. Molarity is mole of solute per volume or liter of solution. So what is the molar concentration? If you know the answer already, you can put in the chat box. Okay, no Shohada said 0.5. Others? 0.5. Firuzah said 0.5. Yes. You have mole of solvent over liter of solution. So you just straight away divide the values to get 0.5 molar. Okay. Another question. What is the molar concentration of sodium chloride if you have 0.5 mole of sodium chloride in 0.5 liter of solution? Okay, using the same approach, try to calculate. Okay, Shuhadat said 1 molar, Puishan 1 molar, Nurain 1 molar, correct? Okay, so the answer is 1 molar. Okay, now, next, what is the molar concentration of sodium chloride if you have 10 grams of sodium chloride in 1 liter of solution? Given the formula mass for sodium chloride is 58.5 gram per mole. So here in example 2, there might be 2 steps that you need to do. The first step is you need to find the mole because mole is not given in the question. You want to find molarity. So based on the definition of molarity equal to mole of solute over liter of solution, you need to find the information for mole of solute. Okay, you already have liter of solution, so you need to find mole of solute. So from the formula mass, you can get the mole. Okay, you can get the mole. The formula mass is 58.5 gram per mole. So you times with 10 gram, you cancel gram and you leave it with mole. It's 0.17 mole. So you can substitute 0.17 mole into the equation for molarity. Then you get 0.17 molar. Okay. All right, next, how many moles of hydrochloric acid are present in 2.5 liter of 0.1 molar HCl? So go back to the definition of molarity just now. Molarity is given, volume in liter is given, so you need to find the moles. Okay, 0.25 mole of HCl. Okay, am I too fast or are you okay with this pace?
Okay.
Okay. Okay, all right. Next example, what volume of a 0.1 molar NaOH solution is needed to provide 0.5 mole of NaOH? So you have the information for molarity and mol. So you need to find the volume. Okay, so you use again this equation or this formula and you get 5 liter. Hopefully you answer correctly. Example 5. How many grams of copper sulfate are needed to prepare 250 ml of 1 molar copper sulfate? So you have the information. Again, back to the definition of molarity. Molarity is equal to the mole of solute over liter of solution. So you have here volume. However, the volume is in milliliter. So you need to convert it into liter. Okay, because of the definition for molarity. Okay, so you have volume and you have molarity. From there, you can find the mole. From the mole, you can use formula mass to find the mass of copper sulfate. Okay, anyone got the answer yet? You can type it in the chat box. Anyone got the answer? 39.9 gram, said no Shuhada. Anyone else? Right. So for those who has not gotten the answer, the approach is we have to use the formula for molarity. Molarity is equal to mole per liter of solution. Mole of solute over liter of solution. So we already have the information on molarity. We already have information on volume. From there, we can find mole. From mole, we can find gram by using the formula mass. Okay, all right, good. All right, we go to the next example. We have 117 gram of sodium chloride dissolved in water to make 1 liter of solution. What is the analytical concentration of the solution? Given here, molecular mass of NaCl is 58.5 gram per mole. Okay, so what is the approach you use? You already have the volume. You already have the mass. What information do you not have? Okay, you write down the formula for molarity. Molarity equal to mole of solute over liter of solution. So, first, you have to find out what is the mole. Okay, you have to find out what is mole. You already have liter, you don't have mole, but from mole, you can get the, from the formula mass, you can get the mole. Okay, mole is equal to mass of NaCl over formula mass of NaCl. This is another equation or another formula that you have to remember. We're going to use this a lot in solving analytical chemistry problem. Mole equal to mass per formula mass. Okay. So we have here mass given in the question, which is 117. And we have formula mass given as well, which is 58.5. So you can calculate the mole, which is 2. Okay. From the mole, you can calculate molarity. Molarity equals to moles, which is 2, divided by liter, 1 liter. Okay, so you have 2 molar. Okay, all right, another example. This one has been given answer. 294 gram of um, sulfuric acid dissolved in water to make 1 liter of solution has an analytical concentration of how much mole per liter? Okay, so this is the same approach that you will use. From the information given, you can find the mole, which is mass per formula mass. You are given in the question, the mass is 294 gram and the formula mass is 98 gram per mole. From there, you can cancel gram and you leave with mole, 3 moles. Okay, from this answer, you can go back to the formula of molarity, which is moles of solute divided by the liter of solution. That will be 3 mole divided by 1 liter equals to 3 molar. Okay, the same approach with example 6. Now, what is this is another concentration unit. It is seldom used compared to molarity. Molarity is more common. However, you need to know as well formality as one of the concentration unit. Okay, formality is formula units regardless of the chemical form of your substance per liter of solution. Okay, formality is the formula units per liter of solution. Formality of a solution may be defined as the number of gram formula masses, the number of gram formula masses of the ionic solute dissolved per liter of the solution. So this unit describes how to make a solution, not what exists at equilibrium. For example, if you have sodium hydroxide prepared from sodium hydroxide solution prepared from sodium hydroxide solid or pellets, okay, and you already weigh out the sodium hydroxide pellets to make the solution. It's the gram of the sodium hydroxide per liter of the sodium hydroxide solution. Okay. This unit describes how to make a solution, not what exists at equilibrium. And formality is also called analytical molarity. So the difference between formality and molarity is that you can express the molarity of the different ions individually. Okay, and the formality is the entire compound irrespective of ionization. For example, 1 formal solution of CaNO3 is 2 molar of nitrate or 1 molar of the whole substance. Okay. Okay. Another unit of concentration is normality. Normality is the number of equivalents of solute per liter of solution. Okay, formality just now is the gram of ionic substances dissolved to make the solution, but normality is the number of equivalents of solute per liter of solution. So the equivalence actually depend on the reaction taking place in the solution. For example, it's different for acid-base reaction, oxidation reduction reaction, and also electrolyte concentration. So for acid and base reaction, for example, when we deal with acid, one equivalent means 1 mole of hydrogen ions because we know the active part of acid is the hydrogen ions. So one equivalent of acid means 1 mole of hydrogen ions. Okay, and in base, in acid-base reaction, one equivalent is 1 mole of hydrogen ions in acid or 1 mole of hydroxide ion in the base. However, when we talk about oxidation reduction reaction, it's no more hydrogen and hydroxide ion. One equivalent is 1 mole of electrons because oxidation reduction reaction is about the transfer, the movement of electrons. And then for electrolyte, for determining electrolyte concentration, one equivalent equal to 1 mole of charge. When we mention or when we use normality as the unit of concentration, it must be specified with respect to a definite reaction. Okay, for example, normality for the acid-base reaction, normality for the oxidation reduction reaction. Okay. Normality is similar to molarity, moles of solute per liter of solution. However, instead of the entire solute, the normality is based on the number of moles of the active part of the solute, which is called a chemical equivalent. For example, when we talk about acid, the chemical equivalent is number of mole of hydrogen ions, and the base is on the hydroxide ion. Let's say we deal with hydrochloric acid. So when we talk about chemical equivalent, it's mentioning the moles of H plus ion in the HCl, not the whole HCl. Okay, that is normality. Now we move to another unit of concentration, which is molality. Molality and molarity is not the same. Molarity is represented by capital M and molality is by small m. Molality means moles of solute per kilograms of solvent. If you notice that previously we talked about the amount of solute in a solution, but when we deal with molality, it's about moles of solute per kilograms of solvent. Okay, solvent again is the solution that you use to dissolve the solute in order to obtain a solution. Okay, this is one example. What is the molality of 6 moles of substance X dissolved into 200 grams of methanol? So the solvent here is methanol and substance X is the solute. Okay, so referring back to the definition of molality, molality is moles of solute over kilogram of solvent. So you need to change the unit of mass of solvent. Here 200 gram, you have to convert it into 0.2 kilogram of solvent. Okay. And then you get the molality, which is 30 m. Then we move to another type of concentration. Excuse me. Okay. Right. Okay. parts per million. The thing that you have to remember or memorize is ppm is always equal to milligram per liter or microgram per milliliter. Okay. And the definition of ppm or parts per million is weight of substance divided by the weight of solution times 10 to the power of 6. Okay. Okay, this is the same. For parts per billion, it's weight of substance divided by the weight of solution times 10 to the power of 9. That one is parts per billion. And parts per billion is nanogram per liter. Sorry, microgram per liter or nanogram per milliliter. Okay, example. Let's say you have a sample weighing 1.3535 gram containing 0.4701 gram of iron. Calculate the percentage of iron in the sample. Calculate the content of iron in parts per thousand and parts per million. Okay, here you have here you have 3 items to be calculated. First, the percentage of iron in the sample. Okay, percentage of iron in the sample, meaning to say that mass of iron in the sample, which is 1.3535, you times with 100%. Then you get the percentage of iron. Can you do that? And type in the chat box. Percentage of iron is equal to the mass of iron divided by the mass of sample. Okay, anyone has the answer yet? Okay, correct. It's 34.7%. Okay, so how do you calculate parts per thousand? This one is wrong. Sorry, yeah? A moment, please. Where's my parts per thousand? Okay, when we talk about parts per thousand, it's 10 to the power of 3. Eh? So here you have to recalculate it. Okay, and then to calculate parts per million, mass of solute over the mass of sample times 10 to the power of 6. Okay, so here's the difference between the calculation. This is weight to weight percent calculation. Weight of solute divided by the weight of sample times 100%. Parts per thousand, weight of solute divided by the weight of sample times 10 to the power of 3. And for parts per million, the weight of solute divided by the weight of sample times 10 to the power of 6. Okay. Okay. Now, we move to another unit of concentration, which is percent concentration. There are 3 types of percent concentration, which is parts per 100, okay, which can be expressed in three types of percentage. Either you can use weight percent, which is weight to weight, mass of solute over mass of solution times 100%, which we have covered just now, or volume percent, which is volume to volume. You have volume of solute over volume of solution times 100%. And for this one, weight per volume, which is mass of solute over volume of solution. Okay, this is volume of solution, not volume of solute. Please make amendments on your note. Okay, this also times 100%. Okay, please take note, yeah, about this one. Okay, example 9. What is the weight to weight percent of an aqueous ammonia solution at 14.3 molar with density of such and such? Okay, so you are required to calculate the weight to weight percent. What is the formula for weight to weight percent? It's the mass of solute over the mass of solution. Now you need to find out what is the mass of solute, what is the mass of NH3, and what is the mass of aqueous ammonia solution. Okay, NH3 solution. So the first step is for you to find out the molecular mass or the formula mass of NH3, which is 17 gram per mole. From there, you can find out the mole of NH3. From mole of NH3, you can find out the mass of NH3. Okay, step 1 and step 2, we have already done it in our discussion for some of the examples for molarity just now. Okay, mole is equal to mass per formula mass. Mole is equal to mass per formula mass. Okay, so from here, you get this one. Okay, you get mole. Sorry, yeah. Oh, okay. 14. Okay. Mole here is coming from the formula of molarity. Molarity equal to mole over liter. So you have already molarity 14.3. You have already the volume, which is 1 liter. It's 14.3 mole. Okay. Where did you get 1 liter? You assume it is 1 liter based. You assume the calculation is for 1 liter based on the given density. Okay. All right. And the next step is for you to calculate what is the mass of solution. You are working on 1 liter of solution just now. So based on 1 liter volume, you times with the density, you get 900 gram. So you already have the mass of solute and the mass of solution. Then you can divide it times with 100% and you get 27%. Okay. Right. What is the molar concentration of an aqueous ammonia solution with density of such and such and 27% weight to weight? So this is just a backward calculation from example 9. Okay, you were given the density and the weight to weight percent. And you have to find out the molarity. So the calculation is just backward of what we have discussed in example 9. Okay. The bottom line is you have to find out the molarity based on the information of mass of solute and mass of solution. Okay. Now we move to volume percentage. What is the volume to volume percentage of ethanol in a solution prepared by mixing 5 ml of ethanol with enough water to give 1 liter of solution? So the first thing you have to do is to identify how to calculate volume to volume percentage. So the formula is volume to volume percentage equal to volume of solute divided by the volume of solution. So you need to find two things. First, the volume of solute, which is 5 ml of ethanol, and the volume of solution, which is 1 liter. However, you have difference in the unit of the volume. You need to convert it into the same unit. Either ml convert to L or L convert to ml. So you have to calculate based on the same unit, and here you get 0.5 volume to volume percent. These are the examples of how we use different percent concentration. Let's say we have hydrochloric acid solutions supplied to our laboratories. They are usually sold in weight to weight percent. For example, if you see the label on HCl bottle, 37%, it means that they are 37 gram of hydrochloric acid in 100 gram of hydrochloric acid solution. So in order to calculate the molarity, you need to know the density of the solution, just like example 9 and example 10 just now. Okay. Sometimes people confuse over the use of percentage unit. Sometimes they thought that weight to weight percent, volume to volume percent, weight to volume percent is equal to each other. Okay, actually they are not. Let's say we compare 5% weight to volume of ethanol to 5% volume to volume of ethanol. 5% weight to volume of ethanol means we have 5 gram of ethanol as a solute in 100 ml of ethanol solution, which is the solution. Okay, when you times with 100%, and you get 5% weight to volume of ethanol. Okay, so 5 gram of ethanol here equals to 0.1 mole of ethanol per 100 ml. Okay, let's say you are working with 100 ml of ethanol. You use it as the basis of your calculation. So when you convert gram to mole, you times it with the formula mass. You divide it with the formula mass. So from there, you get the mole, 0.109. What about 5% volume to volume? Volume to volume means you have 5 ml of solute divided with 100 ml of solution times 100%. If you take out the 5 ml of ethanol and you convert it into mole, you have to use density of the solution, which is ethanol, and then times with formula mass of ethanol. From there, you get the mole of the ethanol containing in 100 ml of ethanol solution. So if you compare 5% weight to volume and 5% volume to volume, you will find out that 5% volume to volume has less concentration compared to the 5% of weight per volume. Okay, so be careful. You have to understand and you have to identify which percentage are they referring to. Okay, when it appear in a questions or in any analytical chemistry problem. Okay, now we move to stoichiometric calculation and factor label method. Just now we have learned some units of concentration, how they are defined, and how do we use them. Okay, now I'd like to move to how we use stoichiometric approach in solving analytical chemistry related problem or calculations. There are actually 7 steps to do this. Whenever you get analytical chemistry problems or analytical chemistry questions, you need to follow these steps in order for you to ensure that the calculation is correct and give what the question asks for. Okay. The first step is for you to write a balanced equation for the reaction. Sometimes the question did not give you any chemical equation or any chemical reaction equation. But from the question itself, you have to derive the equation and then balance it. Okay, so make this the first thing you do whenever you get any stoichiometric problems, any analytical chemistry problems to be solved. Okay, first you write a balanced equation for the reaction involved. Then you calculate all the molar mass of the substance involved in the reaction. For example, reactant A and reactant B reacts to produce product C and product D. So you have to calculate all the molar mass for A, B, C, and D. Okay. And then from the questions, you need to write down all the given quantities, and you also have to write down the unknown quantities, the thing that the question wants you to find, or the thing that is required for you to find the final answer. Okay, so you write down all the variables given, all the values given, and the unknown. Okay, number 4, you have to set up conversion factors using the stoichiometric coefficients in the balance equation. That's why balancing equation is the crucial part of solving any chemistry problems. When you have your equation balanced right, you can have the correct coefficient which you can use um, as a conversion factor when you do your calculation later. Okay. Now look at this example. Suppose you have 4 grams of hydrogen gas reacts with excess oxygen gas to produce water. How many grams of oxygen are required and how many grams of water can be made? From this question, it's not giving you any chemical reaction or any chemical equation. So what you do is you have to identify that when we talk about hydrogen gas, it's always H2 and oxygen gas always O2. And you know that oxygen gas is given in excess. Okay, so you do your equation H2 plus O2 becoming water, which is H2O. From that chemical equation, you write a balance equation. Okay, you balance the equation. So when you have balanced the equation, it goes like this. You have a coefficient in front of the each of the substance, which is the reactants and the product. Okay. When you already have this coefficient in front of your reactants and product, when you have it correct, you can it can help you to calculate correctly. Okay, all right. And step number 6, always check your calculations to see 2 things. The first, the unit cancel to get the desired unit. That's why you need to include all the units. Let's say mass is gram, have to include the mole, you have to include mole per liter if necessary, gram per mole if necessary, to make sure that you don't miss any units cancellation and you can get the unit the unit of your final answer correctly. Okay, and the second thing that you need to make sure is that the total grams of the reactants should be the same with the total grams of the product. Okay, for example, here you have 32 grams of oxygen and you have 2 grams of hydrogen. Okay, so 4 grams of hydrogen. You have 4 grams of hydrogen. You have 32 grams of oxygen. So on your reactant side, you have 36 grams of hydrogen and oxygen. And on the product side, you have 36 grams of H2O. So you have a balanced mass. mass balance between the reactants and also the products. So by this way, you can ensure that you have done your calculation correctly. Okay. And step number 7, you note the rationale followed for all stoichiometric calculation. Let's say you have the number of moles for substance A. If you want to get the mass of substance A, you are going to need the information on the molar mass of substance A. The same goes with substance B. If you want to get the moles of substance B, you have to know the mass of substance B and also the molar mass of substance B. That is why in one of the steps just now, which is step 2, okay, you need to calculate all the molar mass in order for you to easily identify the moles and the mass of your uh, reactants and also your products. Okay, and when you balance your equation properly, you can get the correct coefficients for you to calculate the moles of each reactants and your product. Okay. Okay, that was just now explanation on the steps that you can use in order to solve any chemistry related problem, any stoichiometric calculations. So you will be using the next 2 hours of this afternoon to do the exercise for learning unit 2 and apply all these 7 steps in order for you to calculate uh, and solve the calculation problems. All right. So now we move to the last section of our lecture today, which is preparation of solution. Okay. There are two types of methods for preparing solution. Number one, we prepare solution from pure solids, as in experiment 1, when you read and you learn the procedure of preparing sodium hydroxide solution from sodium hydroxide pellets. Okay, so that is one type of solution preparation. You prepare your solution from pure solids. And another type of solution preparation is by diluting your solution from stock solution. Okay. Now, these are the steps for preparing solutions from pure solids. First, you have to calculate the amount of solid required. How do you calculate the amount of solid required? You have to go back to the definition of molarity. You have to be able to define how many molar you want to prepare your sample and how much, means how many liter, what is the volume. Okay, when you already know the molarity and the volume of your uh, solution that you want to prepare, from there you can get the mole of the solute required. From the mole of the solute required, you can get the mass of the solid or solute required. Okay. So after you have calculated how much amount of solid required, you weigh out the solid, you place the solid in a volumetric flask. For example, if you want to prepare a 500 ml sample or solution, you use a 500 ml volumetric flask. And if you want to you want to prepare 1 liter of solution, then you use 1 liter volumetric flask. Okay, so when you already place the solid in the volumetric flask, you fill the flask with half full of water and you mix the solution until you mix the solute and the solvent until they dissolve, until the solute dissolve in the solvent. And then when that already happened, you fill the mug with water and you invert the volumetric flux to mix them. Another way for you to prepare solution is through dilution. Many laboratory chemicals, such as acid, they are purchased as concentrated solution, or we can also call this stock solution. For example, hydrochloric acid, they are normally supplied whether in 37% or 12 molar. 12 molar is a very concentrated acid. The same goes with other acids and base. So what we do is that we use dilution technique to dilute the sample and make a, a less concentrated solution. Okay. So stock solution here is a solution of known concentration from which other solutions are prepared. Okay. More dilute solutions are prepared by taking a certain quantity of the stock solution and diluting it with water. When we deal with dilution, there is one formula which we need to remember, which is M1V1 and M2V2. M1 is the molarity of the initial solution, original solution, or what we call it as a stock solution. V or volume here, V1 is the volume of the initial or original or the stock solution. M2 is the molarity of the resulting solution or the diluted solution, and V2 is the volume of the resulting or diluted solution. Okay, remember, 1 is for the initial, 2 is for the resulting or the diluted solution. Okay, and moles of solute before dilution is the same with mole of solute after dilution. Even though you dilute a solution, the moles are not changed. The only thing that changed is the volume and also the concentration. However, the moles, they remain even after dilution. Okay, so from there, we have this equation M1V1 equals to M2V2. Okay, let's look at this example, last example. 53.4 ml of a 1.5 molar solution of sodium chloride is on hand, but you need some 0.8 molar solution. How many milliliter of 0.8 molar solution can you make? In this case, we already know the volume for stock solution is 53.4 ml and molarity for stock solution is 1.5 molar. So we already know M1 and V1. We also already know that we want to make a 0.8 molar solution, means this is V2. V2 is the concentration of the diluted solution or the resulting solution. So we already have M1, V1, and V2. M2. We already have M1, V1, and M2. Now we need to find V2. So we use M1, V1, M2, V2. So V2 here is 100 ml. Okay. Alright, so you can use the same concept to answer this question. In this question, you have stock solution 1 molar, means this is M1. And then how many ml are needed to make 100 ml of 0.75 molar, meaning to say that this is the resulting volume 100 ml and resulting molarity 0.75. So you have M1, M2, and V2. So you can find V1 from the equation M1 V1 equals to M2 V2. Okay, I think that's about it for today's lecture. We have covered three things. The first thing is different units of concentration. Second thing is the steps, the 7 steps you use in dealing with any stoichiometric calculations or any analytical chemistry problems. And then number 3, solution preparation. There are two types of solution preparation. First, you prepare it from pure solid, and another one from dilution of stock solution. So I think that's all that I can share for this afternoon. If you have any questions, you can leave it in the chat box or you can ask in the group. What I want you to do for this coming 2 hours is for you to do the ELIP activity, the exercise, and also the study question. Okay, try to do it today so that you can use whatever we have learned just now quickly so you remember better. Okay, and the best thing, you don't have any more homework to do, any more assignment. Okay, so you can spend these 2 hours to do that, and you can ask question anytime. Okay, that's all for today's lecture. Thank you for coming. If you have difficulty to scan your attendance, you can write your metric number in the chat box. But if you can scan, this is the QR attendance I'm sharing here. Thank you very much and see you next week or in the chat group. Thank you, everyone.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.